All right, here we go. So this is 2013 AV number 5, but this is for BC just because area and volume is not in the AB test, but it's on the BC test. So this is for you guys, BC. Okay, you're given these two functions. The region R is bounded by both functions, and first part, they just want you to find the area of that region. Now, you have to be able to tell which is the top function, which the bottom function. So here, if you think about it, like the parabola should be facing up. So this is going to be our F function, and this is going to be our G function. So you could see the top function is G of X, bottom is F of X. And remember, when you're doing area, right, between two curves, okay, you have your intersection, and then it's top minus bottom. Right, so in our situation here, when we're looking for the area of that region, I'm doing the integral from 0, right? So you see, where does the x start? 0 to 2. Top function is the cosine curve minus the bottom function Okay, so just be careful of a couple things, the order that you get it in, and also the subtraction with the multiplication distributive property. The next thing is your antiderivative, so it's going to be 4 is just a constant. Remember, do the reciprocal of that coefficient inside, right? So that's going to be 4 over pi. And your anti of cosine is sine. Leave the angle inside. If you have to, you can do a u sub there. All right, your antis here are going to be, remember, 2x cubed over 3 minus 3x squared plus 4x, right? And then we're evaluating from 0 to 2. Okay, so the 0 looks pretty good because that's going to cancel everything out. Sine 0 is 0. If you're plugging in 2, right, this is going to become 16 over pi. If I plug in 2 here, I get 2 times a quarter, that's 1/2 pi. So that's going to say 1 times 1, right? So 16 over pi minus, plug in that 2. Right, so I'll get 8 times 2, 16 thirds, minus the 12 plus 8. And then, yes, it would have been minus 0 if you plug in the 0. So this is 16 pi. Let's see, that would be 4 thirds minus 4 thirds. And you can leave it like that. Okay, so that's area. All right, now I'm going to stick with this same graph that we have there, right? And now what I want to do is write an integral expression that gives the volume of the solid generated when rotated about the horizontal line, y equals 4. So you get this line here, y equals 4. We are rotating it around, okay? Now with this one, let me just get a red marker. Okay, and you can see now with this rotation around the line y equals 4, we have to figure out, is it washer or is it disc, right? So remember, disc, the way you can remember disc is it touches the line of rotation, or it's on the line of rotation. So disc on line of rotation. washer is not on line of rotation, right? So the other thing that if you notice, this one is going to be washer, right? Because even though it does hit the line, it's not lying on that line of rotation. So we have that there. Now, when you're doing washer method, right, we have still our intersection values. And then you have your big radius minus your small radius, and then dx or dy, okay? So because we're perpendicular to that line, right, when we draw our rectangles, then we know it's dx because it's a horizontal line. Perpendicular would be the vertical, so we're going to use dx. All right, so for a big radius, you go from the line all the way to that furthest curve would be your big radius, and then you're looking for the distance there. Your small radius would just go from the line of rotation to the closest curve, okay? So let's see, so big R, right, is going to be the distance from here to here. So 4 minus your function, f, okay? So our function f was at 2x squared minus 6x plus 4. All right, we could simplify that down, right, because the 4's are going to wind up canceling, so we have 6x minus 2x squared. Okay, so that would be our big radius. Okay, our small radius is going to be from this line of rotation to that first curve it hits, or g of x. So our small radius is going to be 4 minus the cosine, which is the 4 cosine 1/4 pi x, okay? Oh, and then don't forget, I'm sorry about the pi, don't forget pi. So here, right, we got pi. My intersection is still going to be the same because it's 0 to 2, right, because we're using the x. And then big radius, which is 6x minus 2x squared, the whole thing squared, minus 4 minus 4 cosine 1/4 pi x, the whole thing squared, and we're dx, okay? So let's just write that a little bit neater, right? So it's going to be pi 0 to 2, 6x minus 2x squared, the whole thing squared, minus 4 minus 4. Okay, and there is your setup for the volume rotated around y equals 4. All right, the last part of this question is now we're using this, the region is the base of a solid, and then the cross sections are going to be perpendicular to the x-axis. So anytime you hear that, you want to draw your rectangle perpendicular to the x-axis. And we want to write an integral. Oh, the x-axis is squares, and we want to write an interval that gives the volume of the solid. So remember the couple things. If you have a square, right, it's really just the top function minus the bottom function squared, right? Dx or dy. If it's an equilateral triangle, right, remember the rule, root 3 over 4, right, and then top minus bottom. If it's a semicircle, pi over 8, top minus bottom squared dx. And then make sure you have the other ones as well. But we're just doing the square, so I'm just doing the first one. So here the setup is going to be, what's my top function would be g of x this time. So still 0 to 2 because it's x-axis. Top would be g this time, so 4 cosine 1/4 pi x minus the 2x squared minus 4. 6x plus 4. And then everything squared, okay? And that would be the setup there. Just be careful of notation, all right? Okay.